Hi guys, happy Monday. As promised, I have a video here for you. Bet you didn't think I'd make one, but I did. Just because this lesson is so important and I really want to make sure that you have a good explanation of these two problems rather than just looking at my work. Although I did a pretty good job on my worked out examples, which I uploaded to my website for you guys. So take a look at that too if you want in addition to this video. But anyway, we have the last two problems from Unit 5.6 here to talk about. And so just a recall from Friday, 5.6 is all about this idea of optimization. So we're trying to maximize or minimize some value in a context, of course. So in this example that we just barely started talking about on Friday, we have this training facility and you want to get your kayak to the clubhouse and you're trying to, let's see, what are we trying to do here? We are trying to minimize the amount of time that it takes us to reach the clubhouse. So it says here, your training facility is situated along the straight shoreline. I think the training facility is supposed to be that house-looking thing. You row your kayak out 2 miles from the nearest point on the shoreline and then row 6 miles down the beach each day to train for an event that includes rowing and running. If you can row at a rate of 3 miles per hour and jog at a rate of 5 miles per hour, what is the least amount of time required to reach the clubhouse? How far from the clubhouse should you beach your kayak? So we have this diagram here, which we set up. And so we're trying to minimize time and we're given information about distance and the rate at which they can travel. So we talked about how the formula relating those three things is distance equals rate times time. And since we're minimizing time here, I rearranged time to be distance divided by rate. And then we came up with our primary equation, which is the total time it's going to take us can be calculated by adding together the time it takes to row plus the time it takes to jog. So then we have to figure out, well, how long will it take us to row and how long will it take us to jog? And we calculate that by taking the distance rowing divided by the time rowing and the distance jogging divided by the time jogging. So in the diagram, I made x the distance along that lower part of the triangle, and if that whole distance is 6 miles, then the other part would be 6 minus x. The reason why I put x on the triangle part of it is so that when you use the Pythagorean theorem to get the length of the hypotenuse, which represents the distance you kayak, that will be a lot nicer if you just use x there as opposed to the expression 6 minus x. So that's where I got the square root of x squared plus 4 squared. It would be a squared plus b squared, 2 squared plus x squared. And then you would take the square root of it because that would be c squared and we want c. So the square root of x squared plus 2 squared, and 2 squared is 4, of course. So that's how we came up with this equation over here. The total time it's going to take us is going to be the row time, which is row distance divided by rate of row, plus the jog time, the jog distance divided by the rate at which you can jog. And then over here I wrote down that the constraint for x would be 0 is less than or equal to x, which is less, or 0 is less than x, which is less than 6. And you know what? I think we can even make these inclusive, at least on the 6, because if you travel, if you make it 6, you want to beach 6 miles. You want to beach your kayak 6 miles from the clubhouse. That would mean you pull your kayak straight here. And so you would still be doing some kayaking and some jogging. The reason why we don't want to include 0 is because if we included 0, then that would mean you're pulling your kayak all the way up to the clubhouse and you wouldn't be doing any jogging. And that is outside the domain because you want to train for jogging and for kayaking, and so we're not going to include 0, but we will include 6 in our domain. And that's going to play an important part at the end when we test to see where the minimum occurs. Of course, it's going to erase that part. Okay. So that's why I'm including that here, so that we can see how and when that happens. So I'm just going to quickly fix this here with X. Okay, so let's go ahead and continue on with this problem now. We've got our primary equation and we've set up our constraint. So now our next step is going to be to differentiate our primary equation. Okay, so to do that, I am going to call this T prime of X. And I'm putting the of X in there to make it clear that this is a function. And so this is really like 1/3 of the square root of X squared plus 4. So this is going to be 1/2 times 1/3, and that 1/2 comes from this being really x squared plus 4 to the 1/2 power. So then this is going to be x squared plus 4 to the negative 1/2 power. Then we have chain rule. So derivative of x squared is 2x plus 1/5, and then derivative of 6 minus x is just negative 1. Okay, so let's obviously rewrite this nicer. This is going to be, well, the 2's will actually, 2 and 1/2 will cancel out. So this is going to be x over square root of, or 3 square root of x squared plus 4. I took care of the 1/3, I took care of this piece here, I've got the x, okay, minus 1/5. Perfect. And so we want to now find the value of x that is going to minimize this. So again, to do that, we set the derivative equal to 0. And when I do that, I'll add the 1/5 over. So x over 3 times the square root of x squared plus 4 equals 1/5. And I'm just going to solve this like it were a proportion. 5x equals 3 times the square root of x squared plus 4. And I'm going to go ahead and square both sides of this to get rid of that square root. I'm going to get 25x squared equals 9 times x squared plus 4, which is 25x squared equals 9x squared plus 36. So subtract 9x squared, we get 16x squared equals 36. Add by 16. And simplify that, and you'll get 9/4. Ooh, this is actually really nice. And you didn't even need to simplify that. I guess I could have seen 36 and 16 as both perfect squares, but so are 9 and 4. So when you square root this now, you get x equals, and that will be plus or minus 3/2. Well, since we can't have negative distance, we are going to assume the positive here. So we're going to say x is positive 3/2 or 1.5. So we have a possible length here that will minimize time. The first thing we should do, though, is justify that 1.5 is indeed a minimum. And to do that, we'll make a sign chart. So T prime and T 1.5. Now this is where you're going to want your graphing calculator. And because we're going to be using both the original function and the derivative function at points in this problem, I am going to store both of them in my calculator at once while I'm over there. So I'm going to go ahead and put the original time function in as y1 and the derivative function over here in as y2. So popping over here to the calculator, I'm going to go to y equals, and in y1, I said I was going to put the original function. So I'll want to set a parentheses around each fraction, or you can use the fraction bar by doing the alpha y equals to bring up that fraction, and that might actually help you not mess up parentheses here. So it's going to be square root of x squared plus 4 over 3 plus, and I'm going to grab another fraction here, 6 minus x over 5, and that's my original function. And now I'm going to put my derivative function in to y2. So again, I'm going to pull up a fraction here, and it's x over 3 square root of x squared plus 4 minus 1/5. And there we have both the function and the derivative. Now, for our sign chart, we want to use the derivative to figure out if we have a minimum here. And so I'll probably use 1 and 2 to test values left and right of 1.5. So since I put the derivative in y2, I'm going to go alpha y2 of 1 and alpha trace y2 of 2. And I do get a negative and a positive, which is good to start here, because that proves that 1.5 is a relative minimum. Now, of course, with optimization, we're looking for more than just relative minimum. With optimization, you're looking for the absolute minimum or absolute maximum on the given interval. So we can say that t of 1.5 is definitely a relative minimum. So now we want to find what the actual time would be at 1.5, but we should also test the endpoint. Remember, we included 6 as a possible domain, as a possible member of the domain. So we should test that since it's an endpoint and absolute extrema can occur at endpoints. So we'll test 1.5 and 6 and see which one of these actually minimizes the time that it takes that person to row and jog to the clubhouse. So I'm going to pop back to my calculator, and now to find or calculate time, you're using the original function. So that's why I just stored that one in there earlier. So this will be y1 of 1.5 and y1 of 6. And so, we can see that the grand winner is 1.5, because that will minimize time, because we get a less time there. So I'm going to come back here and say that at 1.5, the time it's going to take is 1.733 hours. And at 6 miles, the time was 2. Oh shoot, I forgot what it was. It was like 2.1 something, I think. Hours. Doesn't really matter because it's more. Okay, so then of course we should write a nice justification sentence, because the problem asks what is the least amount of time required and how far from the clubhouse should you be to your kayak. So we've got 2 pieces of information here. Let's put it all together in a nice cohesive sentence. Okay, so I'm going to say the least amount of time is 1.5. Oh, actually 1.5 was the miles, wasn't it? Not the hours. Okay, so let's erase that. And drop back to the pen here. Is 1.733 3 hours. If you beach the kayak, 1.5 miles from the clubhouse. Since t prime of 1.5 equals 0, and the sign changes from negative to positive here, t of 1.5 is less than t of 2. That was the other contender. All right, cool. Done with that one. All right, next one, last one. Says that Justin Case found a 4-foot piece of wire left on a construction site. He is learning about optimization and calculus and wants to cut the wire to create a circle and a square. How much of the wire should be used for each shape in order to maximize the total area? Okay, so we're looking at a circle and a square. We are given information about the length of wire, which tells us that we're going to need some perimeter equations. So perimeter of a square and perimeter of a circle, which is called circumference. But we're trying to maximize area. So we're going to need the 2 area formulas as well. So this problem is actually going to have 4 different equations involved, which is kind of a lot. So we'll have to take this one step by step. So first of all, we're trying to maximize area. So total area is going to be found by adding together area of the circle plus area of the square. So for a circle, area is found by taking pi times the radius squared. For a square, area is found by taking the length of a side squared. Now, because we're dealing with the length of the wire, we should also jot down our perimeter equation. So for circle, perimeter is circumference, which is 2 pi r. And for a square, perimeter is 4 times the length of the side, 4 sides. So back to our primary equation over here, total area is going to be pi r squared plus side squared, which is kind of not great because, again, that contains 2 different variables within the equation. So we're going to have to do some rewriting of variables in order to get this all in terms of either radius or side. So let's talk about what we know here. So we know that in order to, well, let's talk about our domain. Let's talk about our domain here. With 4 feet of wire, a square has to have all 4 sides equal. That would mean that the most any side could be is 1. And if all of the sides were 1, then we wouldn't even get a circle because all 4 feet would be used on the square. And then also, if the length of a side of the square was 0, that would mean that we would have all of the wire to use on a circle. So we're going to restrict our domain in terms of S, the side length of the square. So we're going to say that our domain for S is between 0 and 1. And I'm going to say inclusive because it's possible that we might achieve maximum area if we don't create a circle or a square and instead use all of the wire on just one of the shapes. So that kind of dictates what we're going to have to rearrange our formula in terms of. We're going to need to get R in terms of S since we're restricting our domain with respect to S. So let's come up with a secondary equation now. Our secondary equation is given to us by the constraint. The constraint is that we have 4 feet of wire. And so that dictates perimeter, right? So 4 feet of wire is going to have to make up the circumference of the circle, 2 pi r, plus 4 times the length of the side of the square. Okay, so if we want to get r in terms of s, that means I need to get r alone. So to do that, I'm going to subtract 4s and then divide by 2 pi. So the radius is 4 minus 4s divided by 2 pi, which everything is divisible by 2. So 2 minus 2s divided by pi. And again, we needed to do that because we're stating that our domain depends on the side length s of the square. And so in our area formula, we have to replace r with something in terms of s. So I'm going to rewrite my equation now. Oops. As area with respect to s is going to be 4 times, instead of radius, instead of r, it's going to be 2 minus 2s over pi squared. That's my 4r or pi r squared plus s squared. Now, differentiating that is going to be difficult. So I'm going to start by doing some rearranging here. And so what I notice, first of all, or just in simplifying, is that this is going to end up being pi squared down here. So, or maybe I should square let's go ahead and square the top first. I think it'll be easier for you to see. So area based on side is going to be pi times 4 minus 8s plus 4s squared over pi squared plus s squared. Now, what I was getting at is that this is actually, we have a pi out front and a pi squared in here. So we can simplify a pi there. But we're still going to end up with a fraction over pi, and it'd be nice if we can combine. So I am going to give this a denominator of pi, which means I have to give it a numerator of pi as well. So that's going to give me the area with respect to the side length of the square is going to be 1 over pi. I'm going to factor that pi out, that 1 over pi out, times 4 minus 8s plus 4s squared plus pi s squared. Okay. Now, not super noticeable, but enough noticeable that I'm going to do something about it, is we have 2s squareds. So technically these are like terms. So if this was like 2s squared plus 4s squared, we could combine it to 6x squared, 4 plus 2. But it's 4 and pi, and since you can't combine those because pi is an irrational number, that's 4 plus pi s squared. So I'm going to rewrite this as 1 over pi times 4 minus 8s plus 4 plus pi s squared. Because I think it'll be easier to differentiate that. All right, so let's do the differentiation now. So a prime based on s is c 1 over pi times derivative of 4 is 0. So negative 8 plus 2s times 4 plus pi. Okay. So that's my derivative. Now again, when is derivative maximized, or when is this maximized or minimized? Well, when the derivative is undefined or equal to 0. Well, this is never undefined, so let's set equal to 0. And now if you were to add, or I'm sorry, multiply pi to both sides to get rid of that 1 over pi, 0 times pi is still 0. So this is going to be negative 8 plus 2s times 4 plus pi equals 0. Of course, I'm going to add my 8 over, and I'm going to divide by 2. And then s is going to be 4 divided by 4 plus pi. So at this point, I'm going to get an approximation for that, and I'm going to store that value in my calculator, 4 divided by 4 plus pi, because that's going to come up and be really important later. So I'm going to clear all this out. 4 divided by 4 plus pi is 0.560, and I'm going to go ahead and store that in as variable a to use later on. 0.560. Okay, so jumping back over here, 0.560. So we have a couple of things we need to do now. We need to, first of all, justify that this is a maximum because we're trying to maximize area. And then we also have to test our endpoints because those are also possible. Even if 0.560 is a maximum, it would be a relative maximum. We need to see if either endpoints is more maximum. That's not really the right way to say that, but yields a larger area because that would make it an absolute maximum on the closed domain. So let's go ahead and do our sign chart here to first of all justify, see if 0.560 is a relative maximum. So a prime in a of 0.560. So I'll probably test 0.5 and 0.6 as those are really close. Now at this point, I think I'm actually going to go to my calculator and store in my original area function and my derivative. So I'm going to use this as my derivative, and my nicest area function might actually be this one right here to type prior to combining the 4 plus pi, just so I don't make a mistake. But okay, so I'm going to go and store those into y1 and y2. And so clear out these, and I'm going to do the original area function in y1. Of course, they both start with 1 over pi, and I'm going to use that fraction feature. And instead of s, we have to use x, right? So I'm going to do 4 minus 8x plus 4x squared plus pi x squared as my area function. And then I also need the derivative function. So 1 over pi times negative 8 plus 2x times 4 plus pi. Okay. But now let's remember what we were trying to do. We're trying to prove that 0.560 maximizes area. So we need to use the derivative for that. So y2. And I'm going to use the stored value. So I stored that in A, so alpha A. Oh, well, obviously this should give me 0. Duh. We wanted to test values to the left and right. So to the left, and again, this derivatives in y2 would be like 0.5. And to the right, I'm going to use 0.6. And I get a negative and a positive. Well, that's actually quite interesting because that is showing that this is actually a minimum. And our goal here is to maximize area. So that must mean that this is not the value for us. If we were trying to minimize area, that would be one we would explore. So since that is probably not going to be an option, we are going to want, and this I guess would be, I don't know, I guess our derivative would have been step 4. Our justification table here would be step 5. So let's call this step 6. Means we want to do some testing of our endpoints. So let's find the area at 0, the area at 0.56, even though we know that's a minimum, just to prove that it is minimum, and area at 1, since that's the other endpoint. And so I stored the area function in my calculator as y1. So y1 of 0 yields a total area, because now remember this would give us the square an area of 0. So this would be the area of just having a circle. An area at a length of 0.560 yields an area of 0.560. Interesting. Okay. And an area, if we make the side length, of the square 1, meaning no circle, all square, gives an area of 1. Okay, that makes sense because if the side length of the square is 1, 1 times 1 is 1. So what I'm actually seeing here is that the maximum area will occur if we have a side length of the square at 0, meaning no square, and we use the entire wire to create a circle. Okay? So let's go ahead and put this information on our screen over here. Area with 0, 1.273. Area at 0.560 was 0.560, and the area of the side length of 1 is 1. So here's our maximum area. And of course, now let's write a nice conclusion to this problem. So if the length of the square is s equals 0, meaning we use all wire on creating a circle, area will be maximized at approximately 1.273 square feet. This is an endpoint confirmed by derivative test and candidate test. Remember candidates test all the way back in 5.2. Okay, so the first derivative test actually proved that our critical point was a minimum, not a maximum. And then the candidates test is what proves that one of the endpoints was the absolute maximum on the domain. So there you have that. All right, so those last two problems are good. And so the rest of the time today, you can use to work on the 5.6 assignment. At least try, I would say a good chunk of the problems. I'll get my answer key up to that, or an answer key. And on Wednesday, then you guys will get a practice test, and the test will be on Thursday. So spend some good time today working on the conclusion of 5.6, and I will see you all on Wednesday. Feel free to pop in Tuesday if you have any questions on anything. Otherwise, I will see you guys in class on Wednesday. All right, happy Monday.